In this video, we are going to talk about the steel as a structural material. We'll go through a bit of history of steel manufacturing processes, and also we'll go through the properties of different types of steels as well. Steel is no doubt an essential part of our modern civilization. Due to its excellent strength to weight ratio and its versatility, durability and ductility, steel is very critical in construction, machinery and manufacturing industries worldwide. In 2019 alone, 1.87 billion tons of steel was produced around the world. More than 50% of the steel produced goes into the building and infrastructure industries. Steel is produced from iron ore. Iron forms the 5% of Earth's crust, and it is the fourth most abundant element after oxygen, silicon, and aluminium. We have been using iron since 2000 BC, from the beginning of Iron Age. In ancient times, iron ore was heated in charcoal fire in bloomery furnaces. The charcoal reacts with oxygen, generating first carbon monoxide and then carbon dioxide. This produces wrought iron, which is a spongy, porous mass of iron with very low carbon content, around 0.02 to 0.08%. Wrought iron has high densities of impurities called as slag entrapped in it. The impurities were removed by heavy hammering to produce iron with very low carbon content. Wrought iron is tough and workable, and most of the metal produced and used during the Iron Age was wrought iron. But the production of iron in ancient times was severely limited as high temperature could not be achieved in bloomery furnaces. In the 18th and early 19th centuries, blast furnaces were invented in Europe. Blast furnaces made it possible to heat iron ores at very high temperature and to produce iron in large quantities for an industrial use. At high temperature, iron absorbs carbon rapidly, and the higher carbon content lowers its melting point, resulting in molten and castable iron. During the heating process, reducing substances such as limestone is added to facilitate the removal of impurities from iron ore. The process of melting the metal out of its ore and using suitable reducing substances is known as smelting. Molten iron can be directly cast into molds to produce desired shapes. Thus, it is also called as cast iron. The molten iron can be poured to produce an intermediate product known as pig iron. Cast iron has very high carbon content, around 2 to 4%. Thus, cast iron is very hard and brittle and is not malleable. Iron produced before mid-19th century was mostly cast iron and was used in construction, especially in making rails. And in 1856, Sir Henry Bessemer, a British engineer and inventor, developed a method where hot air is blown through the molten pig iron and limestone to reduce carbon and other impurities. It produces steel with reduced carbon content between 0.2 to 1.5%. This process of steel production is known as Bessemer process. When the carbon content is low, steel gains its ductility and hardness. This makes steel suitable for the use in construction material, as a construction material. By the late 19th century, Bessemer process was largely replaced by open hearth process. It was invented by a German engineer called Siemens. Open hearth process could produce steel with low nitrogen, and it allowed precise quality assessment. This process uses shallow open hearth furnaces where solid and molten pig iron and scrap metal is melted with limestone. This production process is, however, very slow and required external heat input. Steel used for construction of rails, bridges, machines, and vehicles in the 19th century and 20th century were produced mostly from Bessemer and Siemens processes. By late 20th century, open hearth process was mostly replaced by more efficient basic oxygen steelmaking or BOS process or electric arc furnace or EAF processes. In modern steelmaking, BOS and EAF together accounts for more than 98% of the total steel produced in the world. BOS process is very similar to Bessemer process, but in this process, the pig iron and iron scrap is converted into steel by blowing pure oxygen over the molten pig iron instead of blowing air like in Bessemer process. Pure oxygen at high temperature is blown on the molten metal through these vertical water-cooled lenses, and oxygen combines with carbon and other impurities to purify steel. This oxidation reaction are exothermic, that means it generates heat. Hence, no external heat is required in the process. Lime-based fluxes are added, which removes the impurities in the form of slag. BOS converter is then tilted to pour steel into the steel ladle. This process is called as tapping of steel. BOS process is very simple and flexible. It is the main bulk production process used around the world for refining iron ore into steel. It also uses 25 to 35% of steel scrap in the BOS vessels. Electric arc furnace process, on the other hand, essentially uses scrap steel to produce new steel. In the EAF process, scrap metal and limes is heated by means of an electric arc. Steel scrap and lime is melted using electric arc produced by these electrodes. Other metals, if necessary, are added at this stage to form special steel. Oxygen is blown into the furnace to remove the impurities like aluminum, silicon, manganese, phosphorus, and carbon. Metallic oxide thus formed are removed as slag. After removing the slag by tilting the furnace, the molten steel is removed. EAF process is used for making special quality steel such as stainless steel by alloying iron with other metals. Iron is alloyed with chromium, nickel, and carbon to produce stainless steel, which is resistant to corrosion. EAF processes uses 100% scrap metal, which reduces resources and energy required to produce steel. And also the oxidation reaction is exothermic, which further reduces the energy required to melt the scrap metal. So we have looked into a bit of history of iron making processes. Let us now look into the properties of different kinds of iron produced in these processes. The first one we will look into is a wrought iron. Wrought iron is relatively pure iron alloy with very low carbon content. The carbon content in wrought iron is very low, at around 0.02 to 0.08%. And it contains traces of slag around 1 to 2%, which gives this fibrous look for wrought iron. Tensile strength of wrought iron along the grain ranges from 310 to 380 megapascal. Wrought iron is pretty strong in tension along the grain, but it is weak in the tensile strength across the grain. The world famous Eiffel Tower in Paris was built in 1889 using wrought iron. And with the production of steel with better structure performances, the use of wrought iron is now mostly limited to decorative purpose only. Cast iron, on the other hand, has relatively high carbon content, around 2 to 4%, compared to wrought iron and steel. With this high carbon content, cast iron is easy to cast but cannot be worked. Again, due to the high carbon content, cast iron is very hard, brittle, and not malleable. In the late 18th century, cast iron was used in construction of bridges and buildings. It is very strong in compression, but it is weak in tension. Hence, cast iron is mostly used for making arches and columns where we don't have any tensile stresses. But due to its low tensile strength and brittle nature, cast iron was replaced by steel by the end of the 19th century for structure uses. Steel has much better structure performance compared to cast iron, like ductility and high tensile strength. Cast iron is still, however, used for making cookware, piping, and engine blocks. As discussed earlier, pure iron with a very little carbon content is ductile and malleable, but it is soft, whereas cast iron with very high carbon content is tough but has low tensile strength and brittle. So Something in the middle, the carbon steel, on the other hand, is an alloy of iron containing carbon in the range of 0.12% to 2%. Based on the carbon content in steel, it can be classified as low carbon steel, medium carbon steel, and high carbon steel. Changes in carbon content in steel changes its properties like strength, ductility, and toughness. Steel with carbon content less than 0.25% is classified as low carbon steel. Low carbon steel is also known as mild steel, and it is the mostly commonly used steel. It is used for making automobile chassis, cookware, pipelines, and also in construction industries. Mild steel has good ductility, weldability, and strength, and it is also less expensive as well. It, however, has a poor corrosion resistance, and it must be painted or protected against corrosion. Steel containing 0.3% to 0.6% carbon is classified as medium carbon steel. Most of the structural steel used in the construction industries are either low carbon or medium carbon category. The increase in carbon content in steel increases its strength and toughness. Steel containing carbon in the range of 0.6 to 0.9% carbon is classified as high carbon steel. High carbon steel is very strong and is used for making springs, high tensile strength pre-stressing wires for pre-stressed concrete, and high strength bars. And steel with 0.96% to 2% carbon is classified as very high carbon steel, and that's extremely strong but is very brittle. Steel containing other elements such as nickel, chromium is called as alloy steel and have specific applications. Steel alloy with at least 11% chromium is called as stainless steel. Chromium in stainless steel reacts with oxygen in the atmosphere to form a thin layer of chromium oxide on the surface of the steel. This thin passive layer formed on the surface of the stainless steel makes it highly resistant to corrosion and stains. Stainless steel is used in construction industry mainly for aesthetic reasons and for special structures which require high resistance to corrosions. Stainless steel is quite expensive, so they have very specific application only in construction industries. And a good example is the crown in the Chrysler building in New York is made of stainless steel. Structural steel used in construction industry is mainly low carbon and medium carbon steel, as mentioned before. The molten steel is mainly produced from BOS and EF processes now, and the molten steel produced from these processes is either poured through the ladles to cast ingots or is continuously cast into the solidified semi-finished products like billets, bloom, or slab. Billets are long metals with square cross-section, as you can see here, or round cross-section, and with area less than 230 square centimeter. Billets are used to hot roll into bars and wires. Blooms, on the other hand, have cross-sectional area larger than billets and goes through the hot rolling process to produce different structural shapes like channel sections or eye sections. Slabs. These are the flat and wide rectangular metal sheets and are processed into sheet metal plates, pipes, and tubes. Structural steel with required shapes is then produced through hot rolling and cold form processes. These are the example of steel billets, hot steel billets, and steel bloom process produced through the continuous casting process. Structural steel with required shape is then produced through hot rolling or cold form processes. In the hot rolling process, billets or blooms are reheated above the recrystallization temperature of steel, which is around 1200 to 1300 degrees centigrade. The red hot metal is then pushed through the rollers that squeezes the metal into desired shapes. It can be eye sections or channel section. It depends on the profile of the rollers. The structured steel members in the hot rolling process are used to produce various sectional shapes such as wide flange section, as you can see here, eye section, or sheet piles, channel sections, or rail sections as well. Steel produced through hot rolling process are relatively cheaper than cold formed steel. Cold formed steel, on the other hand, are produced by rolling or pressing the thin sheets of steel sheets through rollers or press brakes at the room temperature to produce the lightweight steel sections. Cold formed steel sections are usually used for lightweight and short span structure, which requires better durability and dimension precision. Precise dimension sections can be achieved in cold formed sections compared to the hot roll process. As the hot roll process, the members tend to shrink after cooling. So better precision can be achieved through the cold form process. Cold formed steel sections are usually used in low-rise, light structures, space frames, or in storage racks. They are also used as joists and purlins, studs, and decks in high-rise structure, along with the hot roll section as the main framing systems. Cold formed sections are also widely used in roof or floor decks and wall panels, which carry load as well as provide surface to attach the flooring and roofing materials as well. So these are some examples of the cold formed sections used as storage racks and floor decks. Here is another picture from the Science Place building for the lecture theatre at JSU. As you can see, the cold formed sections are used as the purlins, and the hot roll section are used as the main girders and the columns. These videos, you can have a look at these videos, which shows the hot roll steel manufacturing process and the cold form steel manufacturing processes as well.
Steel is highly resistant to shaping when it's cold, and for that reason it is generally rolled whilst it's hot. To make sure the steel is at the correct temperature for rolling, it is fed into a furnace. Here it travels through several temperature control zones until it's at the correct temperature and ready for rolling. Whatever the product, the principles of hot rolling are the same. Steel is squeezed between rolls until the final thickness and shape are achieved. To do this, the rolls must exert forces of tens of millions of newtons, equivalent to a weight of thousands of tons. The rolls, therefore, run in massive bearings, mounted in housings of enormous strength and driven by powerful electric motors. These are known as mill stands. The layout of a rolling mill can vary from a simple single-stand mill to several stands positioned either side by side or in a line. The mill rolls themselves can either be plain for flat products such as strip, used for products such as cladding, or profiled for sections, beams and columns for use in construction. Mill stands have various roll arrangements depending on the product being rolled. The simplest arrangement is a two-high stand, used mainly for long products such as sections. For light sections and bars, three-high stands are sometimes used, with the steel passing one way through the bottom gap and back through the top gap. Four-high stands have two work rolls in contact with the steel, supported by larger backup rolls to prevent distortion caused by the rolling face. These give greater accuracy for rolling flat products, such as plate. Universal beam mills include stands with both horizontal and vertical rolls bearing on the steel simultaneously. Rolling processes are computer controlled and monitored up to 50 times per second. Despite the huge scale of some mills, accuracy to plus or minus 50 microns can be measured. The rolled steel is then cooled in a way appropriate to its end use and prepared for further processing or dispatch.
And now for the cold form steel, here is another video from YouTube again on showing how the cold form steel are produced.
Cold formed sections are used for a number of different applications, primarily associated with either the building envelope or light steel structural elements used in walls, partitions or floors. For building envelope, narrow strip steel is rolled into the sections required for purlins or sheeting rails that support cladding and sheeting. It is also pressed to form gutter profiles and flashings. For light steel framing sections, the narrow strip is rolled into C-sections that are built up into walls or whole modules before delivery to site.